começarmos a sessão. And we are live now, and in English as well. Okay, so good afternoon, everyone. First of all, thanks to everyone joining the session. Obviously, the interns, obviously for their presentations, but all the persons that make part of the lab, and also outside persons that also join this public session, let's say, about the summer internship results presentation. So, as you can see in my screen, this is the final event, or the formal final event that takes place in the end of the internships, and basically aims to present all the results, all the achievements, all the thoughts, all the ideas, everything that was developed during this internship by our 5 superstar interns that took their internships for 3 months long. So this journey started at 1st of July, then went to the end of September with some vacations meanwhile, so to chill and relax a little bit. But yeah, it was a great effort, a great experience as well for us. I hope it would be, or it was, a great experience for you all as well. And yeah, we can just kick off this session with some ground rules and also with the agenda for the session. So we have, as I've said before, we have 5 different interns with us. So we have Ana Marisa Macedo that will be presenting graphs for collaborative robotics, flexible task simulation and control. We'll have Liliana Almeida, mostly known as Lily for us, machine learning stack for predictive and prescriptive analytics. We have João Praça with explainable AI for real-time defect prediction and prescription in a production line. We have Rafael Matias, mostly known as Rafa as well. Improvement of Dinosaur tool for easy development of distributed systems and OPC servitization. And we have finally, last but not least, Silvia Rocha, multi-camera monitoring system for object following and obstacle avoidance in collaborative robotics. So, in terms of the agenda itself, we'll be kicking off with Rafa presentations about Dinosaur at 3-ish, okay? 10 minutes past 3, basically, yeah, more or less 10 minutes. Then we'll have Liliana Almeida. Afterwards, at 4, João Praça. At 4:30, we will have Silvia Rocha. And then, last but not least, we have Ana Marisa Macedo at 5 with collaborative robotics presentation. In terms of the format that we have so far for this session, so each presentation will have a maximum duration of 20 minutes. This does not mean that it should take 20 minutes, so take your time. If it's 10, 15, or 5 minutes, it's perfect for us. So maximum duration of 20 minutes. We have, after each presentation, will take place a short discussion with maximum of 10 minutes. Once again, it's a maximum, not the time that it should take. All mics should be turned off during the session. I also advise only the presenters to have the camera on because of mainly bandwidth issues here in the lab. We have a lot of people here in the lab, and we might experience some network bad quality connections. Then all the questions should be asked in the discussion phase. So please keep your questions afterwards or after the presentation. And then all the questions might be asked directly, so in the discussion phase with the mic on or using the chat, okay? So you might also, if you don't want to interrupt, for example, the presentation and want to ask something while the presenter is doing the presentation itself, you can basically just write your ideas, comments, or questions directly in the chat itself, okay? So, this is it in terms of the intro. Once again, thank you all for being here, mainly the interns, obviously, because they are the basically the center of the event and the session itself. And obviously, thanks to all the participants in this session as well that are the non-presenters. So without further ado, Rafa, the floor is yours, or in this case, the screen is yours. So once you want to start presenting, feel free to do it.
Okay, perfect. Thank you very much. Let me see if I am able to share my whole screen. Okay, you should be able to see my screen by now.
Yeah, perfectly.
I'll also ask you, can you hear my voice? I apologize in advance that I won't be having my camera turned on because of internet complications, if that's okay. But as long as you can hear me, that should be fine.
Yeah, we can hear you perfectly, Rafa.
All right, nice. So let me start the presentation. Okay, so as Professor João Reis has mentioned already, I am Rafael Matias, and I will be presenting the work that I have developed during my internship, naming it Improvement of the Dinosaur Tool for Easy Development of Distributed Systems and OPC Servitization. So let's start by talking a little bit about the Dinosaur tool, and we can ask the question, what exactly is it? So according to the description that we also have in our repos wiki and documentation, Dinosaur stands for Dynamic Intelligent Architecture for Software and Modular Reconfiguration. It is a distributed platform that runs at the fog computing level, enabling the pre-processing of data using algorithms that are encapsulated inside modules, and that is function blocks. This reply might have helped understanding a little bit of what Dinosaur is, but let's ask another question and see if we can understand it even better. So why? Why use the application Dinosaur, and why was it developed? Many of us developers, and if there are also for sure other developers who have faced the issue of code reusability. Basically, you want to use some code that you have developed again in a new context, but there's always problems in that new context. You never develop code, or you rarely develop code that you can just simply copy paste and then it's ready to go and ready to be used. Function blocks that were mentioned in the previous slide eliminate that problem. You can you create those function blocks. They are the code that you decided them to be, and then you can easily connect them to other function blocks, rearrange them however you want, eliminate them, add new ones, and it's much easier to reuse code this way. Dinosaur also works in a distributed pipelines manner, and that means that you will be making pipelines of these function blocks connected to each other, and you can distribute them across different devices. So not only your laptop, but if you have a desktop or if you have Raspberry Pis, you can distribute your pipelines across different devices. It follows the IEC 61499 standard, which might help you implement code too, and uses the OPC protocol. Basically, Dinosaur runs a OPC server, and you can host there your pipelines and make methods for them. And you can trigger those methods as if you were triggering that pipeline through an actual network address. More on that later. And finally, if any of well, maybe those applications are a bit hard to get started on, and most of them are not free. And Dinosaur is easy to get started, as we will demonstrate, and is free. So those are the advantages of Dinosaur. And this presentation will mostly consist of the tutorial that we are about to begin. I will be showing you how to set up Dinosaur, making usage of not only the official repository of Dinosaur, but also the one that contains the function blocks that we at the lab have developed. Of course, you can start by developing your own right away, but if not, you have a library full of these function blocks that you can use. You'll learn how to build a pipeline, how to generate OPC UA methods, so those methods that I mentioned, and then how to build an OPC UA method calling pipeline. So we'll figure out what all this means pretty soon. let's start by opening. I've already cloned all these repositories on my local machine, and I'll be accessing the second repository, the one of the function blocks on Visual Studio Code. As I go through this tutorial, I'll also be mentioning what contributions I've made to the program and during my internship. So let's jump over to Visual Code. And here you have the repository, you have the FBS folder, which contains all function blocks. All the files are here. So there's that. And then there's the synchronization program. I've developed this synchronization program, which basically allows you to synchronize these function blocks to any dinosaurs that you might have installed on any device. So you can have dinosaurs, for example, I already have 3 dinosaurs on my local machine, 3 different folders, but you might have folders on remote devices with which you have like an SSS connection, for example, SSH connection. And for those, you can also add the username and password tags right here. But if not, it should look like this. You only need to come here to the config.json file. You specify the location of where you have your function blocks, so our folder right here. You specify the location of the dinosaurs that you are synchronizing, so the ones that are going to be filled with these function blocks, the location and the address, and the username and password if it's an SSH connection. And then you have the strategy. Currently, there's only one available strategy, which is the wipe strategy. I'm basically telling the synchronizer to delete any function blocks that might still be here on these folders. But if you don't want to do that, you can simply delete the tag or just leave it empty without the wipe word. It's up to you. Let's run the script, and it's as easy as just going Python synchronize, and it should synchronize my 3 dinosaurs without a problem. We can actually move on and start up a dinosaur, and then we'll start building our first pipeline. So let's come here to documents and let me choose my first dinosaur. All right, running a dinosaur is also pretty easy. You can just run it with Python core main and it'll be running. The feedback it gives us is not very visual. You'll have a file with the list of errors that you might encounter, but you also have, as you will see later, in the server, in the OPC UA server, you have a list of these errors as well, where you can check them. But yeah, so let's start making our pipeline. In order to build the pipelines, we use a program that's called ForDiac. And I'll just briefly show you one other step that you need to take in order for ForDiac to also know where the function blocks are. By the way, this tutorial might have quite some steps to it, but everything is very well put in the documentation of each repository. So if I'm speaking too fast, maybe because there's a lot of content to cover, or if something's missing, you can always check the documentation and everything will be there. There is a library folder here on ForDiac, on your ForDiac installation, and you can simply create a folder called FBS or whatever name you decide, and just clone the repository right here. It's as easy as that. There's no problem with it, and ForDiac will automatically find these function blocks that you can start dragging and dropping on what we'll see now, the app view. So let me fire it up. And we're using version 1.11. I suggest you use that as well when following the tutorials, because the tutorials were made using this version, so it's easy to follow. Let's just create a new system, and we can call it tutorial. And you have this app view where you'll create the pipelines, but you also have the system configuration where you depict the characteristics of your system configuration. So we are working on a PC, you need to add this mRes property, then you connect it to the network, and now ForDiac knows what the system looks like. So let's make the pipeline. We can come to the FBS folder, we have all the function blocks that we need, and we're actually going to start by creating a pipeline that simply generates 2 random numbers. So here's the function block. Each function block always has inputs and outputs. And here the input is the range, so I'm going to want to be generating numbers that go from 0 to 9. And we have the outputs where our random numbers will be. This pipeline is as simple as this. There's nothing else. It's made up of only one function block. We'll make pipelines that are longer than this, but still, you'll understand the concept behind a pipeline easily with like this. We can map this to the device that we have told for the act before. And it's good to be monitored and watched and tested. So let's do that. Let's monitor the system. Let's watch these values so that we can better understand what's going on. Now we get feedback on their values, and let's deploy the pipeline. So we can make sure here that we are sending it to the right device. So it has been deployed. Everything should be working fine. So a pipeline, basically you trigger one of its events and it will trigger other events showing their outputs, and each output is used for the next one's input. If we go over here and we press trigger event, the event was triggered with the number of 1, and 2 random numbers were generated, 8 and 6. And so here you go, it's your first pipeline, you've made it. Let's go to the second point, which is generating OPC UA methods. So methods that you can check out on the OPC UA server that is running with each dinosaur. Just come over here to the OPC UA folder and grab an info wrapper. As the name suggests, you need to wrap your pipeline or a section of a pipeline with it. So we can connect this event to the event that we want to trigger. So naturally, we want to trigger the run event. And you can connect this event to any of the ending events of your pipeline. Let's map it as well to our device. And let's give a name to this method. So maybe gen for generate. And it should be working fine. Let's deploy it as well again, and you can redeploy as many times as you want pipelines, and the dinosaur is always running. And let's check it out with a OPC UA client. We are using Prozis to check this out, but you are welcome to use any client that you want, as long as you're able to access a certain address and see the properties of the server. By default, dinosaur runs on port 4840 for this server. If we connect, we can see that the server is up. We just check some security things. And here we can see the configuration of our dinosaur. This is something that I also spent some time on during my internship, which was organizing all these folders and information. We can see the function blocks that make up the pipeline. We can see the events and the variables and their values. You can check, do some hardware monitoring, so see how much CPU memory is being used. You can also check the errors that have been produced, and you can check the methods. So here we have our gen method. We can see the inputs and outputs, but let's actually call it right away. So when I call the method, I need to specify the value for the event that I'm triggering. So we'll do it just as for the act did. We'll trigger it with 1. And everything should be working fine. We just generated 2 random numbers, 2 and a 1, and yeah, through an OPC UA method. So OPC UA methods are seen. Let's actually try to call these OPC UA methods through our own pipelines, because if we can do that, then we can encapsulate as many pipelines and sub-pipelines and whatever in OPC UA methods. And each method calls a pipeline, and other methods can wrap them, and it unlocks a lot of potential. So let's try and do that. We're going to create another pipeline similar to this that concatenates 2 inputs as strings. So if it receives 2 numbers like this, 2 and 1, it will generate the string 21. That's called concatenate str. And let's grab an info wrapper. And let's connect it as we did with the other one. And actually, before we move on, let's also fire up two more dinosaurs that we are going to need. So let's just open new Windows, open the dinosaur, and fire it up. So it's as simple as running the same command, although we need to change the ports. Naturally, the other ports are already being used. So this one is actually going to use 61500 to communicate with FortiAC, and the server will run on port 4841. You just need to update those flags and it'll be fine. Now we need the third and last dinosaur. So yeah, here. And just as we did before, let's just increment by 1. So Python core main, and we can do minus B 61501 minus U 4842. Okay, now everything should be working fine, and we have 3 dinosaurs running. Let's tell that to Fordiac. We can move this one over here. Let's repeat the process for 2 more other devices. So don't forget to change 61500 and 1 final dinosaur running on 61501. All right, and all connected to the network. So now we can map this to the second device. Let's give this a name con for concatenate. All right, and now let's see how can we call these methods. I'll push this over here, even actually over here. So you have a function block that, as the name suggests, calls methods. It's the method caller, okay? And it's as easy as just specifying. So we want to trigger the method called gen, and the server URL, I already got it here, so it's easier. Just copy it, but you know which one it is. It's at localhost 4840, and we're going to trigger that method with a 1. And let's just grab another one and make an actual pipeline with multiple function blocks. So naturally, the first input, the first output will be the second's input. So we connect it like so. The run output will trigger the second's function block, so no problem there. This one is going to call the method name con, and similar address, but 4841. Let's grab it to here, it's prettier. All right, let's trigger it with the input event of 1, and let's also wrap this with an info wrapper so that we can call it on ProsIsh and we can better visualize it. We can map it to our last device, and this should be working without a problem. Let's deploy all 3 of our pipelines. As I said, you can deploy and redeploy as many times as you want. And let's check this out on ProsIsh. Let's connect to the last one straight away. So 4842, none. Okay. And now we see that we have a new method. It's called info wrapper because I did not name it. So it defaulted to the name of the function block, but I could have also named the function block right here. Let's call it. So as you can see, it asks for this input variables field. And that's because I didn't fill it in Fordiac. That's also another functionality that was developed. It's not asking for these server URLs because that information is already being told to Fordiac. Dinosaur detects that and doesn't do anything else, but it didn't detect the input variable, so it's asking me to tell him. Naturally, the input variables are going to be the range for the first function block. We know that it's 10, but if it were more inputs, we could add them like so, separated by commas. It's just a 10, so we can even delete the brackets or keep them. It's up to you. And add a 1 to trigger the method caller with, and let's call it. So as you can see, the first method caller returned the 2 random numbers. The second method caller concatenated them, and 53 became 53. So now, not only do we know how to make a pipeline, we know how to generate LPC-way methods, and we know how to call them from our own pipelines. Let's go back to the presentation. So future work, what else can be done in Dinosaur? A lot can still be developed. A good first step could be a transparent distributed cyber-physical system. And what this means is that imagine that you want a pipeline to be distributed across different devices. So the very same pipeline, not different pipelines like we did, but the same pipeline across different devices. You need what are called service interface function blocks. So MQTT brokers to communicate via MQTT with other devices. And the first functionality that we could develop would be to, sorry, it says I have bad network quality. I hope you can still listen to me. So that each dinosaur could still communicate to each other without the need of specifying those function blocks on Fordiac. Then we have the problem of task resource allocation. So one of the big advantages of Dinosaur is really that you can use different devices. You can use a laptop and a Raspberry, like I said in the beginning, all running the same pipeline because of the transparent distributed cyber physical system. With different resources, of course, comes different execution times. So if we want to optimize the execution time of a single pipeline, we need to adapt and see, okay, this device has this many resources, it's better suited to run this function block. So it can make these adjustments while it runs the pipeline, and after multiple runs, it will have enough data to adjust and look for optimal solutions. Or even after enough iterations, we can actually use some hypermodeling and imagine that a new device is added to the system. Then the Dinosaur could somewhat predict what would be the best function block to add to a device that has that many resources based on previous practice. And finally, we could work with time and resource restrictions. So maybe our user wants the pipeline to run under a given amount of seconds, like 5, but any solution that's under that time frame, it's fine. So Dinosaur could go and try to save as many resources as it could under that time frame, so that you can run other pipelines in parallel without wasting too many resources. So that's it for my presentation. Thank you for everyone. Thank you to everyone that's listening, and a special thank you to Professor João Reis, researcher Eliseu, and Professor Gilles for making this internship possible. And I will be replying to any questions that you might have now. Thank you.
Thank you, Rafa. So it was a wonderful presentation. I would say perhaps a wonderful demonstration in this case. So yeah, you developed a lot. That's a lot of functionalities here at Dinosaur. So I would say that initially Dinosaur was still, I would not say a baby, but a child, and now it has grown up very fast during the last couple months, and now we have a very, I would not say Dinosaur on steroids, but something close to that. On steroids would be the implementation of the future work, but yeah, wonderful ideas about task resource allocation, about the transparent distributed cyber physical system and others. So I think it was very, very clear. And yeah, I think we can just open now for any questions, any comments, any doubts. I think that perhaps first I could ask Eliseu for any comment on this, since you was the main person basically contacting with you, supporting you in the Dinosaur side. So Eliseu was one of the first developers of the Dinosaur, and yeah, it was organic for him to support you and supervise your work. So in this case, Eliseu, any thoughts, any words, any comments on this?
Hello everyone, it's a pleasure to be here. Yes, the baby dinosaur is now anti-Rex. Let's say it is growing too fast. It is growing too fast. Yeah. This presentation was very clear. Congratulations, Rafa, for your work. It was a great work. Your presentation and demonstration was very clear. I think from my side, I don't have many questions because it was very clear. I only want to begin the discussion about some points, but it's only to discuss some points, not formal questions about your presentation, because the problem that you are handling, it was very clear to me. The work that you have done, it was very good, and it was very clear the way that you present it to us. Regarding the questions and topics that I may want to discuss here, before you came to work with Dinosaur, the goal of Dinosaur is to develop distributed systems. And in some of the cases, when we have to develop distributed systems, we had to access the machine to modify the code, to update the software that we have there, execute different programs. So regarding your work, how do you feel that the need to access the devices that I have? So for example, imagine that I want to deploy a cyber physical system or a distributed system in 10 different devices. How many times should I need to go to the device? For example, should I need only one time for the installation and then I do not need to access the device anymore times? Can I manage the devices only from my computer? Can I monitor the errors from my computer? How is the current stage in that aspect regarding the monitoring and the developing of cyber physical systems? I don't know if it was clear the question and the topic to discuss to you.
Yes, I think it was. Thank you for the question and thank you for the compliments as well. So yeah, Dinosaur was developed with that in mind, or at least these improvements were developed with exactly that in mind. So when you want to first set up the Dinosaur, you go through those steps of cloning the Git and making sure that it is on that machine. But after that, it's as easy as just using your local machine where you are developing code. So let's imagine, for example, when you deploy, you saw that it was easy to deploy from 4DX. But let's imagine that you want, for example, to transfer the function blocks that you are developing in your own computer to those dinosaurs and have them running those function blocks. That's, for example, what the synchronization feature was for. So from your own computer, be those devices local or remote, and in this case, imagine there are 10 remote Raspberry Pis or something like that, you can just specify their address, the credentials to be allowed to transfer through SSH, and the function blocks will be there. There was also one functionality that I did not have enough time to show, but this allows the Dinosaur to keep running even when there are changes to the function blocks. So let's imagine that I changed the concatenate function block to not only concatenate the inputs, but always add a dot at the end of the concatenation. I could do that on my local computer, activate the synchronization, all those dinosaurs would be updated, and live, the changes would take effect live. So there are sniffers running on each dinosaur, detecting if there have been changes to the function blocks. And if there have, they are automatically updated. So the worst case scenario would be if for whatever reason a dinosaur crashed. Then it would the user would have to manually go to the device and have it run again. Obviously, work was done in that effect as well. So some refactoring and some exception handling was also done during the internship. And yeah, I believe that answers your question.
Yes, can you hear me? Yes, that answers the question, and yes, this is really a big problem that we have in distributed cyber physical systems. I had some months ago one example when I was deploying a distributed system. Without those features, I had to upload to each one of the Raspberry Pis same code, and if I have a mistake in one line, I will need to upload it to update it, and this feature will be very useful in case of time to reduce the time to deploy those type of systems. Thank you, Rafa. Go on, João. Sorry.
Thanks, Eliseu. And obviously, thanks, Rafa, for the excellent reply. So in this case, just to wrap up the discussion part, please keep in mind that we still have our chat live. So if you have any questions during the presentation, you can just place it there, and then we can answer afterwards. But yeah, just to comment before we conclude this discussion part and go to the next presentation. So one point is, Raf only presented a few of the functionalities, let's say, or a few of the work that he has developed. In the beginning, a major code refactoring, let's say, as Raf has mentioned, took place. So a lot of time was analyzing the dinosaur, get familiar with the dinosaur. But yeah, there's a lot of backstage work in the dinosaur that are not related with these explicit functionalities that you can promptly use. This is something to highlight, and I believe that for most of the internships this is true. So a lot of background work, like getting to know the technologies, get to know the tools, get to know into the context of their internships to do the best work possible. So this is obviously to highlight, and yeah, with your presentation, I think all the functionalities were very clear, and the potentialities of the dinosaur are also very clear, and also the clues for the future work are also very interesting, and exploring this in the near future would be very interesting. The other point that I would like to highlight is that one of the things that this OPC UA method caller basically explores or allows in this case is the servitization part. So as Raf has mentioned, you can basically announce one pipeline or one block or pipeline, whatever you want as a service. You might also want to servitize a pipeline of pipelines. So as soon as you can call pipelines wrapped into OPC-UI services, this allows you to basically build several layers of complexity in terms of pipelining and how to develop your pipelines. But one of the things that most attracted me in Dinosaur in the first place is that all the function blocks are developed in Python. And we can also allow to deploy several machine learning, artificial intelligence algorithms in these pipelines. So it was also first thought and designed to be able to deploy these algorithms into the shop floor. We are not talking about servitization in terms of cloud systems because we were running against Google, Amazon, and we don't want that for sure. But once we talk about edge computing, basically IoT devices, processing and deploying machine learning algorithms near to the machine, I think the mindset is a little bit different, and Dinosaur is competitive at that level. Okay, so I think this is unique in this aspect, and yeah, the servitization on the edge level is very good, and it allows a lot of potentials to basically be used in real industrial applications where most of the times cloud systems are not allowed, or if they are allowed, they have a lot of restrictions in terms of how they can use data. So this also restricts the kind of algorithms and methods that you can use for artificial intelligent algorithms. So yeah, this is just to wrap up this with these two points. And yeah, we can move forward to the next presentation. Once again, thanks, Rafa, for your excellent presentation. And now,
thank you.
Yeah, you're welcome. And then we can move forward to the next presenter. So Lily, as we call, the screen is yours. And yeah, I don't know if you, yeah, we can hear you. Yeah.
Yeah.
And now see the screen.
Can you see the screen?
Yeah. Okay. Yeah. All good, Lily.
Okay. Can see still, right?
Yep.
Okay. So what I bring you today, hi, for everything. What I bring you today here is a machine learning stack for predictive and prescriptive analytics. The context of everything developed for this project is based on machine learning operations, also known as MLOps. People may think that a machine learning model can be developed and continue operating forever. However, like every machine, they need to be continuously monitored and maintained over time to see how they're performing and shifting with new data. This is where MLOps comes into action. It can be seen as something similar to DevOps, but in the context of machine learning. So basically, MLOps allows to deploy, monitor, and manage machine learning models in production at scale in a reliable and efficient way. Many companies are increasingly adopting this concept since it allows them to leverage the benefits of machine learning in the real world, allowing fast innovations through a robust machine learning lifecycle management. It works like a bridge between data science and operations teams, as well as other teams, improving their collaboration with each other. MLOps also keeps track of version history of models and also their performance to enable auditing and allow a faster intervention when models start to degrade. The purpose of my internship was to come up with a flexible machine learning stack that handles big quantities of data and that processes it in both streaming and batch. This is the basis of a project being developed for Zeugma and Siemens. The main goal was to define technologies for the database, for data flow management, and for MLOps. However, there are a huge amount of technologies, so the task for deciding each technology should be chosen, it's not that easy. Just in this image, there are a big amount of technologies, but only for concerning machine learning and artificial intelligence. So trying to find this huge amount of technologies, it should be hard. But we, after some research and analyzing some advantages and disadvantages of those technologies, we came up with this first approach, using these 4 different technologies. We can start with Kafka, that is a distributed event streaming platform consisting of servers and clients that communicate via TCP, and it is used in the project to process stream data before they go into the pipelines. The next one is MLflow, which keeps track of the models by logging parameters, versions, metrics, and other relevant information that might be useful to the user. Airflow consists of a platform to schedule and monitor workflows, and it looked like a dynamic and scalable option to manage machine learning algorithms and the part of MLOps of the project. Lastly, we have MongoDB. That is a NoSQL database with high flexibility since it saves data in JSON files. And this way, we can have small changes in the data structure that don't compromise all the system. In this project, we used the community version of Mongo. Having all the technologies decided, I started developing some actual pipelines with a model and data from another project of the lab that was only used to validate the structure. And what happened with this stack was that the pipeline's tasks took too long to be allocated and executed. It could take like several minutes from the moment the pipeline started until it was finished. So it was obvious that this wasn't the perfect solution if we wanted to have a stack that was able to stream data and obtain an output as fast as possible. Analyzing the current technologies, every platform seemed to do what they were expected to do without any problems except for Airflow, which was responsible for the high expense of time. Airflow is not made to deal with streaming data, so it is not its main goal to make everything run as fast as possible, but more to make sure that the tasks are done and they are done in a specific order. Besides that, it also doesn't allow event-driven pipelines or streaming, and it wasn't also fond of passing data from one task to another, which can be useful for our case. For all those reasons, new platforms were searched to try to replace or at least complement Airflow. In this table are presented some of those platforms that were found and could be interesting to do that job. To help better understand those characteristics, I tried to check the presence of the most valuable features for our projects, like streaming, event-driven, cron jobs. And the language, the preferred was Python, since it was an easy and well-known language. And the pipelines that were already developed in Airflow were in Python. So if we kept the language, it would be, we could reuse the code and we could save some time. For a lot of these platforms, it was hard to realize if they had what we needed without really testing them. However, there were too many to analyze and test. So I only tried to look and understand if there was any that was worth trying to at least test. And in the end, the one that looked more promising was Prefect. Prefect can be seen as an improvement over Airflow. It is also a workflow management system to control pipelines. It also allows to schedule through cron job and other ways and trigger pipelines. But unlike Airflow, it has a much faster allocating system that allows a faster processing of the pipelines. For this reason, we stayed with this platform and tested it out with success. Although most of our needs were met, the stack still didn't allow data streaming. So after some research, we found the platform Faust to try to suppress that need. What Faust does is to listen to Kafka topics, and whenever the data arrives, it processes it the way we want. In this case, what it does is to trigger the pipeline corresponding to the topic in which the sample arrived. Imperfect then implemented 3 different pipelines. The first one is a predictive pipeline to detect if a failure in a machine is going to happen or not. The second pipeline is for optimization, which is triggered every time the prediction results in a failure, and returns a recommendation of which variables should be changed to avoid the failure state. Like, for example, it could recommend to decrease the temperature by 2 degrees. The last pipeline is responsible for saving everything it receives in the database. It includes the original sample and the outputs from the other pipelines. It should be noted that the database has no defined structure yet, and the data is being kept in tables corresponding to the origin of that data. That means if the data comes from the prediction pipeline as the output of that pipeline, it is saved in the table for that pipeline for now. Now, we will see how those technologies that we talked about communicate with each other. For each pipeline that we already talked about, there is a different topic associated. Since this way of organizing the topics, it makes it easier to know to which pipeline should the samples be sent to. Whenever a Kafka topic receives data, Faust acknowledges it and triggers the corresponding prefect flow. Other relevant information from the pipelines can also be logged into MLflow, like the outcome of the prescriptive analysis or the predictive analysis. So now I'm going to make a little demonstration. Let me just change screen. So we have two main UI interfaces for our system. There's one for MLflow and another for Prefect. The MLflow, as you can see here, has the records for each run that we track, for each moment that we decided to track. And for example, in this record, we can see different metrics for the resulted from the prescriptive pipeline. That means the optimization pipeline. And there are a lot of things that could also be tracked with MLflow. When we're seeing the Prefect interface, we can see here the history of runs that were made, also other summaries, and here we have all the flows that we already talked about. If we go into one flow, we can also see the run history. There were 2 an hour ago, and the other summaries correspond to this flow. If we select a specific run, we can see the tasks that were completed and which one failed, if that was the case, and also check the logs, that the prints that are made in the program during the flow run. So other features that this interface has is to, if we go to a flow, we can run it from here immediately. But in this case, it doesn't really make sense since we don't have data receiving. And we can also schedule it for a specific time or for 5 to 5 minutes or something like that. I can show you how. This is a script to send a sample data to the topic A. That means to the prediction flow and to the database flow. So we can see here the two flows that were triggered by that script, and after some time it will be completed. We can also, if we wanted to create a new pipeline, we could do. We just have to write this line with the correspondent name of flow that we want, and inside of this we can do whatever we want. We can call the tasks that we want. That is basically a function with a tag task, and in the end we have to register it in our project, so it appears on the interface. Let's say now that we want to have a Kafka topic associated with this flow. We have two ways of doing it. We can come to Docker Compose and have here another topic, but this won't work if our system is already running. So if it is already running, we have a command that tells the Docker to create that topic. However, if we stop our system, if we stop the Docker, we will lose that topic, and if we don't put it here, it will be lost, and we have to add it manually again. If we want for this topic to trigger that pipeline that we created, we can come to the script that corresponds to the FOST and have another agent that will be listening to this topic and trigger the flow that has the name we gave previously. Okay, so now going back here to our presentation, sorry. Let me just changes. Okay, so now now we are here, and as the time for development was not that long, and as there is always some space for improvement, there are some points that could be done in the future, and they are presented here without any particular order. One of them is to implement and explore ways to detect concept drifts, that is, to detect when the distribution of the streaming data changes and starts classifying more times wrong than right, which can easily happen with this kind of data and can happen for various reasons. Whenever these drifts are detected, the model should be retrained with the samples that were retrieved until that moment. And for this, a new pipeline can be developed and triggered when there is a drift. Scikit Multiflow is a platform that allows to easily generate data streams from a given dataset and even induce concept drifts. So that would be interesting to implement in our project to see how would the system respond to that drift and just normal data. Lastly, until now, the database structure is not well defined because it can vary from project to project, and we still didn't have access to the data that will be used for this project. So this is a point that should be done when the access to that data is given. We're still looking at the database. A REST API can be useful to access the data from outside of our stack, and it should be explored if already exists one for MongoDB. Otherwise, it should be created a new one from scratch. So this is all for my presentation. Thank you so much for your attention, and thank you so much to everybody in the lab that helped me throughout these months. And yeah, thank you.
Thank you, Lily. It was a wonderful presentation, and yeah, it's pretty tough to choose among all the platforms that are there for data science, machine learning, data engineering, you name it. So there's a lot of things, and yeah, one of the key difficulties, let's say, of this work is that you need not only to choose a technology for pipelines, not only a technology for database, not only a technology for event-driven management, for example. It's basically a myriad of platforms that you should integrate, that you should combine, and you should have a server with a lot of applications that should communicate among themselves. And this is no easy peasy. It's not an easy job. And yeah, it's a lot of testing, as you have said. And yeah, thank you very much, Lily, for your presentation, for your thoughts as well on the platforms. Yeah, just 2 comments about this. You mentioned, and I believe it's mostly true for everything, but at least in this case, it's a little bit more. Necessary, let's say. It's about testing the platform. So you can read as much as you want. I believe that you have read, I don't know, thousands of medium stories, thousands of towards data science stories as well. So a lot of things about multiple platforms. There's also a lot of stack combinations for different purposes of machine learning implementations. Perhaps one stack is specific for streaming problems, another stack more specific for vision systems, another stack for NLP. So it's really, really tough to basically implement and take the most out of these platforms, and mostly to select the best platforms for your application. And in this case, you said that testing is the key for this, because it's really difficult for you to assess. For example, the case with Airflow is the most prominent, let's say, that you expect something from Airflow, you read, it seems good, it seems interesting, it was developed by Airbnb and so on and so forth, so it looks fancy, and then you start running things and start executing things, and yeah, it was, I would not say kind of a flop, but more or less like that. So I would not say flop, it's basically interesting for different applications, let's say this way. And yeah, so is this kind of testing that takes time and is really tough and is really valuable. So you can basically gain some knowledge and gain some intuition about the platforms, and the second iteration is always best than the first one, the third and the fourth, and so on and so forth. So it's kind of difficult for you and for anyone that is not experienced in all these platforms to basically make a good choice at first. And the second thing is this internship as a context, and one of the contexts is so as you saw in the architecture, you could see in the right left corner or upper left corner, you could see one expression that was telling ML Studio. So this is part of a project where we should plug this into a machine, and machine inherently will produce data at a very fast pace. So this is inherently a streaming problem. That's why Airflow in the beginning was not very suitable for this case, because we wanted to collect data, digest data, process this data, and then synchronize this data with a lot of platforms. I would not say the first amount of platforms. I mean, you at first chose, I would say, 99% of the best platforms. They all run well. I think the Airflow, the branding was a little bit best than Prefect, perhaps. But yeah, you tried it out, and then you changed this to Prefect, and it filled our needs, and it's a really nice platform. I really like to see those dashboards running live, so no need to refresh the page the pages we required, or it is required in Airflow. So another plus for Prefect. So all these things should be weighted, all these things should be discussed, and it's no easy job to basically choose these platforms. And yeah, just one small question so we can move forward very fast. We are running just a few minutes late, but just a very fast question. So the same way you have changed Airflow for Prefect, wise choice, it fills our needs, it's really good and up and running very fast and very good. Right now, and as you right now, you are the person that has most intuition and knows the best platforms. Do you feel that some other platform from the ones that you have presented kind of needs some, I will not say some recoding or needs to be replaced by another one? Do you feel like, okay, perhaps if you rethink a little bit about Kafka, we can replace it by this one, or MLflow is not kind of doing anything, so perhaps if you replace MLflow by another platform? So do you have any intuition about the other remaining platforms, or can we give any clues of what's not running very well at this stage and might be replaced in the future, or everything is perfect and the stack is stabilized right now?
Okay, so yeah, Prefect, I think it's really doing what it's supposed to be doing, and it's really good. MongoDB, I think it's also good. I mean, we didn't use it that much because we don't have a data structure, as I said, but I think it's flexible enough for what we want. When we're talking about MLflow, I mean, we didn't use it that much in the project, but I think it can be useful if we want to keep track of the metrics and how are the models performing and so on. So I time. I think basically it's because of Zookeeper, and I think they are removing it from Kafka. So probably it would be better to then improve it, so to update it to the Kafka without Zookeeper. And I think probably it would run better, because so the problems that happened, I think, was from connections with Zookeeper.
Okay.
Overall, I think it's really good.
Yeah, nice.
Working.
Yeah, that's a very good clue to basically remove Zookeeper from the equation. And yeah, and perhaps this would run smoother, not better, because I think everything is running very well. But at least run a little bit smoother without Kafka going down so many times and so on and so forth. So this is the kind of problems that it's a little bit difficult to anticipate when you choose a platform. So the source of problems is so heterogeneous that you basically cannot predict what might happen. Even the necessity to update and refresh the web page to see things changing in pipeline.
No, that was unpredictable.
Yeah, that was completely unpredictable. Yeah, perhaps 15 years ago it would be fine. Yeah, but nowadays it's a little bit unpredictable. But yeah, once again, thank you very much, Lily. It was a wonderful presentation, very clean, very to the point, very informative as well. Thank you very much for your work. And yeah, now we can go and move forward to the next presentation. Thank you.
Thank you.
So as the next presenter, we have João Praça. I believe it's here with us already. His presentation is entitled Explainable AI for Real-Time Defect Prediction and Prescription in a Production Line. Hello, João. How are you?
Hello.
Hi, João.
Can you hear me?
No, yeah. Yes,
okay.
Yes. So yeah, when you feel free to start, just go ahead.
So I'm just going to share my screen. Can you please check if...
Yeah, we can see your screen.
Okay. So as Professor João Reis said, my internship was in Explainable AI for Real-Time Defect Prediction and Prescription in a Production Line. So first of all, I'm going to explain a bit what is Explainable AI, so that for those of you who don't know. So Explainable AI is the process that allows human users to understand and comprehend the output of a machine learning model. So we are able to understand an output given a specific input, and we are able to link them together. This has three main advantages. So it gives us the opportunity to improve our analysis of the model and the data. It makes it easier to explain to people who are not familiar with ML models how the model makes decisions. And it can also help us avoid negative and unforeseen consequences of this particular model. So these three factors of Explainable AI give us more confidence in our model and therefore increase its trustworthiness. So there are some simple machine learning models, such as linear regression and decision trees, which are easier to understand and to explain, and therefore they are called white box models. So we can, in this kind of models, we can easily establish a relationship between the data used to train the model and the model output. So then we can explain it, why the output was given, why a certain outcome was given a specific input. However, there are more complex models, such as deep neural networks, which, although they can be much more accurate, they are much more difficult to understand and to explain. And so they're called black box models. The main challenge of Explainable AI is basically to understand this kind of complex models much more easily and consequently increase our trust in them so that we can understand why the decisions are made based on the input data. So currently there are mainly two algorithms in explainable AI that generally produce good results, whether independently of the model we use and the data set. So those are LIME and SHAP, and first of all, I'm going to talk about LIME. So LIME stands for Local Interpretable Model Agnostic Explanations, and as the name says, it supports explaining individual predictions, so a single sample, by approximating a complex model to a linear model in a specific region around the vicinity of a particular instance. So for example, in this image, we can see a complex function on the left, and the white background means and there is a stroke, and the blue background means there is no stroke. And if we zoom in on a specific region, for example, in this where this pink dot is, we can approximate this region of the model to a linear model so that it is easier to understand, and we can clearly state that the pink dot is in the above the line, the linear line, so we can say that it means there is a stroke. And next, there is SHAP, which means Shapley Additive Explanations. And as the name says, it uses Shapley values to create an explanation. So what are Shapley values? Shapley values are calculated to get the contribution or impact of a feature in a model. So features such as age or gender. So what it does, it compares how the model behaves with and without those features. So for example, it tests how the model behaves with age and with all the other features, and how the model behaves with all the other features except age, for example. However, features can also interact and work together. So, for example, two features only obtain good results if they work together and not individually. So to get the full contribution value of a specific feature, we need to calculate its contribution with every subset of features. At the moment, there are two well-known Shapley values, SHAP implementations. So there is tree-SHAP, which is basically what I just explained. And there is also kernel SHAP, which is kind of a mix between LIME and using Shapley values. Kernel SHAP usually tends to be more accurate, but it also takes much more time to execute. And tree-SHAP also obtains fairly good results. So in the context of my internship, we needed to figure out in real time what were the features that contributed the most for a defect in a wood plate production line. So we've tested these three algorithms on an XGB boost model with the data of the production line, and got the top 5 features that contributed to the most for the model output. Overall, all the algorithms presented similar and apparently good results, and considered features most important, such as the length of the wood plate and time interval between production of 2 pieces. However, kernel SHAP took a very long time to process an explanation. So, and as our goal was to give an explanation in real time, we put kernel SHAP aside. And between tree-SHAP and LIME, both of them gave good results and were fast. And LIME will run in about under a minute, but tree-SHAP gave us an explanation basically instantaneously. So it was considered the best explainable algorithm for this particular case. Next, there was the optimization part of the internship. So what we had to do was to apply these concepts on a wood plate production line, as I said. And in this production line, some units were defective, and our goal was to understand why they were defective, what was causing that defect, and what was the best way to avoid it. And the main challenge of this internship was to create a new algorithm that optimizes the defect samples, that is the features of the samples, and gives us a prescription so that the outcome would change from non-defective to or from defective to non-defective. So basically, analyze a specific sample and adjust some values and give us those values so that we can change those values in the machine, and hopefully the number of defects reduces. However, there was one big conditioning, that was only 5 of all the 30 features in the samples could be modified in real time. So we were very restricted on what features we could change. And furthermore, these features, the values cannot be changed drastically. So as it would either be physically impossible, or they cannot be changed that much in a small amount of time. So we had to create some boundaries and apply them. So there was already a version of this optimizer developed by Artur Freitas from the lab. And the main issue there was, and that we had to solve, was that with the samples that have above 99% chance of being defective. So in these cases, the optimizer could only reduce the percentage of defect from above 99% to about 80 to 90%. And our goal was to get it below 50%, so they could be considered non-defective. So, and also to prevent the optimizer to getting stuck in a potential local minimum, we decided to apply a new strategy. So instead of optimizing all these 5 features that we could change, firstly, we would get the 2 most contributive features from those 5, using the Shapley values given by the tree shap. And then we would optimize only those 2 features and save them in a new sample. And then we would optimize this new sample given now that it is in a new optimized starting point. So hopefully we could escape from this local minimum to a global minimum, and the defect would be much more reduced. So, as I said, we applied this strategy using 2 local optimization algorithms. We used Powell and Neldermead. But as you can see in this table, comparing the rows from the 5 features and 5 optimized with Powell and Neldermead, the results are the same. So this strategy did not alter any metrics at all. Either the average, standard deviation, or the number of, or the percentage of defective, non-defective samples. So this occurred either because there was no local minimum, or it was not, this strategy was not enough to escape from it. So after this, we decided to use 2 global optimization algorithms, dual annealing and Bayesian hopping, so that we can hopefully escape from this local minimum. So dual annealing, as you can see, did not improve the results. It was basically the same as the local algorithms, but Bayesian hopping did in fact improve the results in a significant way. So the average was, for example, around 77, and it reduced to 54%. So, however, we suspected these results. They were a bit too good to be true, let's say. And we inspected them a bit further and realized that the boundaries weren't that we had established weren't being fulfilled. So what we decided to do next was to apply these boundaries in a new cost function in the Bayesian hopping algorithm. So the farther a sample is away from the boundaries, the much higher it is the cost function result, that is. However, in this case, the results were not satisfactory at all. In fact, it was the worst of them all, even the ones from the local optimization. So this is basically what I did in my internship, but there are some next steps that I've already started taking but haven't finished yet. So we can ease a bit of the boundaries by a small percentage, so that we can maybe reduce the percentage of defect a little bit. We could also plot the neighborhood of the worst samples to check for a local minimum. That is, we could select the worst samples, like the 5 worst samples, and generate the neighborhood around it, and calculate the cost function for those in this neighborhood, and then plot it and see how it behaves in the vicinity of the sample, to check if there is a local minimum or if there is no local minimum and is no further improvable, let's say. And after this analysis, we could then improve the Bayesian hopping cost function. So we maybe could change a bit the weights, reduce a bit of the weights, or improve the weights of the boundaries. And also at the score cost, like the result being the percentage, that is, of the defect being instead of 99%, it would be reduced. So higher the percentage, the worst. And basically that is it. I'd like to say thank you for your attention. And thank you to João Reis and Artur Freitas, especially for guiding me and helping me throughout this internship. And that's it. Now I'm open to your questions if you have them. Hope you enjoyed.
Thank you, João, for the excellent presentation and explaining very well the explainability and explainable AI. So basically, it's explaining the explainability process.
Exactly.
Yeah, it was very, very interesting, also a very challenging topic. So this perspective of explainable AI, if you know well, the field of artificial intelligence is fairly new. So 10 years ago or 15 years ago, this kind of algorithms were not in place, and explainability due to the not existence, let's say, yet of deep learning models and more complex black box algorithms. Due to this reason, explainability was not that much important, let's say. I would not say important, but not that explored. But nowadays, I believe explainable AI is a hot topic. Yeah, one might think that for industrial cases or industrial scenarios, explainable AI might not be that interesting, but because there's, I would say, more social and cultural urgent matters, let's say, on how it uses artificial intelligence in society mainly, but also in industry, it's really, really, really important because industry is really the first step of everything that you own, from t-shirts, from tables, from everything you own, basically, should be manufactured somehow. So influencing that and using explainable AI to better understand the processes, better understanding the machines, your equipment, your persons, for example, on the job, it's really, really important. And yeah, great job, João. Now I give floor to Artur for a few comments and few feedback on your work, João. And yeah, Artur, when you're ready.
I'm always ready. especially after such a wonderful presentation. Congratulations, João. It is really a reflection of what you did over the past 3 months. It has been quite a ride. You started indeed analyzing what the heck XAI, explainable artificial intelligence, is all about, and why is it such a hot topic and an open problem right now, not only in the academia, but also in the industry itself. And you explained it very well, and went really through with all the different explanations on which approaches there exist when regarding to black boxes and white and black box models, and why the black box models are critical to be understandable, to be helpful in terms of explainability, so that we can implement them in a real context, in real life, without the risk of not knowing what is going on within the algorithm. You then went to the explanations of the different approaches, the different algorithms that there is in the literature, for example, the LIME and the SHAP. You could even gone a little bit further on the SHAP and just give us some kind of schematics with all the different versions, with all the different approaches. For example, saying which one you ended up using in your work, if it was some version of LIME, some version of SHAP, or something else, which I know you did. And you ended up not mentioning it, I think. I'm not sure about that.
Tree SHAP.
Yeah. Okay. And also, you experimented with a novel algorithm, which is not as popular as LIME and SHAP, and you could have mentioned it, for example, because it's very valuable for the work you've done and for what you are going to develop during your thesis. Is that one thing that is really critical about explainable AI is that none of these algorithms are the end of the road. None of these are the perfect final version, which will solve it all. So we still are looking for improvements, and that's what you did. That's indeed the key aspect of your internship. And the second part in your presentation explained it extremely well, what you went through, the optimization and the prescription issue that you had faced in a concrete problem in the industry, in a manufacturing scenario, and what you went through to try to help the algorithm, the prescription algorithm, to make better recommendations. And how did you do it? By trying to understand how it is working. And you did it by implementing an explainable algorithm. So explainable algorithms are not just to overcome bias, to overcome issues associated directly with human beings, whether or not you're going to receive a credit, whether or not you're going to go on vacation or whatever, but also can be associated with non-human factors. For example, manufacturing, for example, defects. And this was a very interesting approach you did, and congratulations for it. I only have 2 questions for you regarding your presentation. And the first one, again with us.
Could you please repeat? I think it froze the internet.
Okay. I was asking if you could share with us slide 6 again.
Yes. So I don't know which is the 6th one.
That is the 5. So the next one, the results. Okay, perfect. First of all, I would have recommended you to have had some some slide before this one, just stating more clearly what your methodology was. Otherwise, it was really nice. It was very, very insightful, and you went through all the details that you had in your work and all the difficulties that you faced. Now, regarding this, are these percent values, right? Correct?
Yes, they're all percentage. Yes.
Okay. Okay. And you basically said, and very well explained, that the last attempt, the new cost function for the Bayesian hopping, was the worst out of all of those approaches.
Yes.
Now the tricky question. Imagine you're in the meeting room with our client, the guys who kindly gave us this data and this information, and they want to ask us, what would you recommend us? What method would you recommend us? I don't think, and apologies if I was mistaken. I don't think you just gave us some overview on the benefits or pros and cons of the best approach that you found among all of these ones.
Well, first of all, I would not choose a global optimization algorithm because, a dual annealing is basically the same as local algorithms, but Bayesian hopping, either of the versions, one is not fulfilling the boundaries, so I don't think it's acceptable because it's unfeasible. And the new cost function has worse results than the local algorithms. So either between Powell or Neldermead, as the results are the same, I would either recommend one of those with all the features optimized at once, because it didn't make a difference. So it was just more time consuming using the optimized version. So yes, I would probably recommend either Powell or Neldermead using the all at once, let's say, optimization.
Okay, perfect. I think the job is yours. João, that's it from my part. I don't know if you want to add anything.
Thanks, Artur, and thanks, João, for your explanation. So it's a little bit weird to call João when you have two Joões in the presentation. I will start calling Praça. It's easier this way. But yeah, thank you very much, Praça and Artur, for your insightful discussion. Obviously, these points that Artur referred are really, really, really important. And yeah, most of everything, I think this is an area full with potential yet to be explored. So it's not something that you basically grab an algorithm with already proven benefits in many areas or high performances in different scenarios and so on. I believe that this is an open area still. There's a lot of areas to test, a lot of algorithms yet to develop as well. So this is a hot topic these days. This is not a closed area, which means that it's also a good time for exploring new opportunities inside this area as well. One of the things that is that I just wanted to comment, not about the presentation, but about the area itself, for all of you to get the sense of how tricky this is. So explainable AI, it's not basically a supervised algorithm where you have right and wrong. Okay, so this is not the thing that, okay, you run a SHAP, 3-SHAP, Lime, Evade, kernel SHAP, time SHAP, I don't know, whatever explainable AI method you want to run it, and then you have your results in the end. But this is not the case. When you have the results, this is not the case where, okay, this makes sense, or okay, this does not make sense. You don't have the correct answer for this. And one of the key aspects that I would like to highlight is you always need, as always it was required, but specifically for this area, you always need some expertise in terms of the business itself, the core business,
Yes.
where you want to apply the scenario. So it's always necessary, independently of it being explainable AI or data science, machine learning, whatever AI field you are working. Obviously, you would need always someone from the core business in terms of the scenario you are working on. However, in this particular case, I think this is more dramatic, okay? Because you have no clue after you run an explainable AI, it says that, okay, feature 7 and feature 10 and feature 21 is the most important, and then you, okay, either you understand the field and the area, and you are not a data scientist or you are not a machine learning engineering, or if you are really expert in this area, you're not an expert in medicine or in industry or in making, I don't know, electronics or cars, as we have applied these in different fields. I just wanted to highlight this because this is not something that it's that exploratory like unsupervised learning even is. So in unsupervised learning, you explore patterns basically, and then you come up with some clues about the process. This is not even the case. So you just have something, and then you have to basically be or to have a critical perspective about this, discuss this heavily, perhaps rewrite some lines of code, run again. It might get even to the point where you change the algorithm because some things do not make sense in terms of the output, because you have your business saying that answers are wrong and you need to fine-tune an algorithm. So it might get to that point. So it's a very, very open area, applicable to everything. And I would also like to say that this is also a great opportunity for applications like banking, insuring, medicine, all these critical areas that require some sort of auditing. So you need to basically say why you are doing that decisions. You are legally obliged to do this and to give these answers. This is basically a huge opportunity for this area. And yeah, I will shush now. Thank you, Prasa, again for your excellent presentation, your smooth presentation with all the results presented. And yeah, thank you again. We now move forward to the next presentation with a little different application scenarios, let's say, and not too much different from what we have seen so far in terms of research area. But now we go more into the robotics area with the next presentation from Silvia Rocha, with a presentation entitled Multi-Camera Monitoring System for Object Following and Obstacle Avoidance in Collaborative Robotics. Silvia is already with us, so when you're ready, Silvia, we can start.
Yeah, I think that I'm already sharing the screen, right?
Yeah, right.
Okay. So, good afternoon, everyone. My name is Silvia, and I'm going to present to you the multi-camera monitoring system for object following and obstacle avoidance that I developed throughout the past few months. So, in this presentation, I will start by explaining the context and motivation for this project, then talk about the multi-camera system setup and integration, move on to the object detection and following, and lastly, we will talk a little about obstacle avoidance. Before anything else, I think it is important to understand why do we need a multi-camera system in the first place. Looking at this image, we can easily understand the limitations of a single camera vision system. In this example, where we are trying to track 3 different people while they are in motion, we can understand that the performance of the system will be low, given that we can easily lose track of one or more of the people with a simple movement. To overcome this problem, which we refer as occlusion problems, we decided to develop a solution where we can use as much cameras as we consider necessary to assure the full coverage given the expected people and objects in a given environment. This will assure that there are no occlusions in the environment and will allow us to increase the performance in tasks like tracking or obstacle avoidance. So, how do we start? To achieve this, the first step was the camera SDK configuration and the parameter exploration to find the best trade-off possible between precision and performance, so that we are able to develop a system that is in real time. But at the same time, we are able to assure some accuracy and precision in the movements that we are trying to track or the obstacles that we are trying to avoid. Afterwards, we proceeded to assure a way of acquiring parallel images of the multiple cameras. We decided that this could be achieved by recurring to the usage of threads. So basically, for each camera detected in the system, we are creating a new thread that will allow us to acquire the RGB images that we want in a given moment from all of the cameras at the same time. At this point, it was time to understand how to calibrate the multiple cameras, because we have cameras that are placed in a lot of different places, pointed at one center point, but we needed to understand how to put them all in the same reference frame. So we did a lot of research in this field. We looked for a lot of different methods, some based in 2D points, some based in point clouds, and we decided to use the iterative closest point algorithm. This algorithm is used to minimize the difference between two cloud points and basically consists of three main steps. In the first one, we find a correspondence of all the points in the source point cloud and try to find the correspondence in the target point cloud. Afterwards, we estimate the combination of rotation and translation using a root mean square point-to-point distant metric minimization technique, which allows us to get the best transformation matrix to align the source points with the matched points. This is an iterative system, as I explained, so we do this for as many iterations as we consider necessary. In the case of this solution, we used around 20 iterations. Afterwards, we have the matrix, but so explaining this, that we did not do this with the entire point cloud because it would be way too expensive. So the way to extract this transformation matrix was basically to get some corresponding points from each of the cameras. So we extracted the RGB image, selected some points, some reference points in each of the images, and then we pass that to the algorithm so that it could work this process. Next, so this is not moving on. Okay. So in the thread that we created for real-time image acquisition for each camera, we extracted the 3D point clouds and the RGB images that I talked before, so that we could then apply open pose. In this image in the slide, we can see the final point cloud. This point cloud corresponds to basically all the point clouds extracted from the different cameras, transformed using the transformation matrix that we calculated using the ICP method. After this first stage is up and running, it's time to face the next challenge: how to process the data that we are acquiring in real time in order to allow real-time object following. In our case, we decided that the object we wanted to follow was the right-hand key point from a person in front of the camera. And so we decided to apply open pose in the multi-camera vision system. Open pose is basically an open source library that allows us to detect key points from the body or some more detailed stuff, but in our case we just wanted the key point, so we had to integrate the open pose with the solution developed in Python, and then we were already able to have a body key point extracted. These key points were in 2D, so we then had to convert that to the corresponding point in the 3D using the point cloud that we extracted. At this point, we already have the 3D point coordinates, but we still need to convert the coordinates from the camera reference frame to the UR5 robot reference frame. For this, we applied a similar technique to the one that I previously explained. So basically, we just put the robot in multiple positions and extracted the position using the UR5 robot controller. And then at the same time, we were acquiring with the reference camera system, we were acquiring the RGB image, and we were extracting the exact same point in the image. We then applied the ECP method as I described before, and were able to obtain the transformation matrix from the reference camera, that is basically camera 0, and the robot coordinate system. So after applying all of these transformations, we now are able to have one 3D point that corresponds to the position in the robot world. The next step, and because in our system we decided to use joint angles instead of passing the 3D points directly, was to implement forward and inverse kinematics for the UR5 arm. The forward kinematics equations are used to convert joint positions into the 3D point coordinates, whilst the inverse kinematics equation can be used to obtain the joint angles that allow the robotic arm to get to the desired 3 point that we chose, basically. So afterwards, we established the remote communication with the UR5 controller and started to use the real-time data processing flow to send real-time positions updates to the controller. We experienced a few different ways of passing this information in order to understand which ROS topic and which parameters were the best to allow a real-time smooth movement of the robotic arm. Here you can see the UR5 robotic arm following the person's right hand movement. There are a little disclaimer, there are some times where it does not work that well because the Z camera finds some noise generated by the metallic robot arm. But in general, we can see that it follows almost in real time the person's movements. And we can just wait a little bit to see a few more of this video. We remember that the point that it's trying to follow is just the right hand, so the rest of the body could move and the robot wouldn't move if the right hand didn't move. And that is basically what we did for object following. For the obstacle avoidance component that was developed, we defined the circular trajectory for the UR arm to follow and used the right hand key point coordinates as the obstacle to avoid. If an obstacle is detected at a certain time, basically what happens is that we calculate if the end effector new position will be inside that object influence radius. And if it is, we understand that we need to change the trajectory of the robot to avoid a collision. In these cases, to calculate the joint angles at each moment, we calculated the repulsive potential for each joint and multiplied it by the respective Jacobian matrix to obtain the final impedance calculation. This impedance is then added to the goal position that we had initially, and that is the sum of those two components is what is sent to the robot in order for it to avoid that collision. So, thank you for your attention and for being here today. I would like to thank everyone at the lab that helped me throughout these months in one way or another, and especially to Liliana for helping me to understand a bit better the robotics universe. I am now open to answer any questions you might have about the work that I just presented.
Thank you, Sylvia. Great presentation about your work. Very challenging work. So everything that goes around robotics is not easy, and it's even more challenging when you try to merge vision systems, more specifically 3D vision systems, with multiple camera. Together with motion control, obstacle avoidance, and obviously following defined objects like your hand, a ball, or some other object that might be defined. Very interesting work, and more to come in the future for sure. And for this case, I would like to ask Liliana Antão for some comment, feedback about the work. She was the one that followed more closely the work from Sylvia. So, Liliana, when you're ready.
Thank you, João. Can you hear me?
Yes.
Okay. So, first of all, thank you to Sylvia for her work. A lot of mishaps with mostly installations, and we know when you try to put together a lot of technologies like OpenPose and the SD-cap of ZED and GPUs, it's tricky, but she managed it. So thank you, Sylvia. Great work, even with all the troubles that you had. Mostly the question that I have for you is more regarding what you developed and its capabilities to expand and deal with more cameras or more objects to follow. So I would like you just for you to say if your developments are ready to, let's say, 4 cameras and tracking 2 objects or 3 objects. Is it possible? Do you think it would still be real time? Do you need to maybe change some of the parameters to keep the real-time constraint, but maybe decrease the performance? What do you think about this?
Yeah, basically regarding the multiple cameras, it's already ready for that. It's not specific to the 2 cameras that I worked with. You can add like as many cameras as the USB port can support, and it will work. Regarding tracking more than 1 person or tracking multiple objects, I don't think that it can track more than 1 object at a time, because the robot is only one, so you can only track 1 thing at a time, I guess, because if you are simulating the movement. For obstacle avoidance, with a few changes, it would be ready to avoid a lot of objects, but right now it's just for 1 object because it was the end part and it was not that well tested, so that part needs to be a little more worked on to get more upfront. But regarding the tracking, I don't see a way for 1 robotic arm to track multiple objects at the same time, because it has to follow just the movement of 1 object. It can change the object, and basically right now if the object that is tracking disappears, it changes to another. If it's of the type that he wants to track, because I decided to just follow people, so it's just open pose. So if 1 person disappears and another appears, it will change to the other person, but it cannot follow 2 people at the same time, or the robot would just freak out. I don't know.
Yeah, the question was more exactly of camera tracking and not robot tracking, but I understood that it's able to track multiple. The camera itself can track multiple. So just one last question. Like you said, let's say you have 3 cameras or 2 cameras, like in your case, and I appear in one, but then I move and I appear in the other. Is the system reliable to these changes? Is it quick to change the camera setting and it works the same way? It's already taking that into account?
Yes, basically the system usually chooses the reference camera, that is the initial camera, but every time the point is not reliable. So in open pose you can have, because we are extracting the whole body, it can be detecting the body without detecting that point. Sometimes that happens, but if it's not detecting that point, it's going to go to the next camera. So camera 1, if you have 5, it's going to check if camera 1 is detecting the point or not. If camera 1 is detecting the point, that is going to be the camera that it uses until camera 1 is not reliable anymore. And basically it just loops like this. If it goes through all the cameras and none of them can find a point, it just waits. It doesn't give up, it doesn't crash, it just stays there waiting in the position that the robot was. It stops and just waits to find the camera again. Regarding precision, it's a lot depending on the ICP algorithm, so it depends on the quality of the points that we give initially. If we just give 4 or 5 points, or if we do the calibration and then move the camera, the movement is not going to be that accurate, because then you just change the camera and it's going to be a movement that is changing the camera, basically, because the point is not going to match. But if the calibration is well done, it will change the camera like in the same time, so it's no delay. There is no delay for changing the camera that it uses, and it will just change and continue running.
Okay, so just one last question, sorry. Okay, now we talked about the vision system. So in your experience regarding what you did for tracking an object and following an object and obstacle avoidance, what do you think it's the critical point in this type of collaborative robotics application? Is it the vision system that is the main key point for the other part of the applications, the object following and the obstacle avoidance, or do you think it's the robot control and the refresh rate that is the key point? What do you think it's the main thing for a safe collaborative robotic application for obstacle avoidance or object following?
I would guess that it's more the vision system, because the reliability, because in the other parts you just work with what you get from the vision system. So if it's not reliable, or if you keep just not getting points, it's just useless, because that is going, if you can only detect a point from 1 minute to 1 minute for some reason, or 10 seconds in 10 seconds, it's not worth to say that you have a real-time stuff if you're not able to detect with precision the points. But regarding the real-time component, there are some calculations that are done outside the vision system. And so it's important to have that into account, because some more complex applications need to be well taught in terms of computational requirements and stuff like that, so that it doesn't lose that real-time component, basically.
Okay, thank you, Silvia, once again. Thank you for the great work and a great presentation.
Thank you.
Thank you, Liliana, and thank you, Silvia, for this interesting discussion about a very challenging topic. Yeah, I don't have any particular comment or a particular question. You are the experts on this area, so I leave these excellent discussions for you. And yeah, once again, Silvia, thank you very much for your presentation. And now we will give floor to the next and final presentation. Once again, last but not least, thanks, Marisa, for all the waiting until your presentation. I hope you also enjoyed the other presentations as well. And we are now moving forward, as I said before, to the last presentation with Ana Marisa Macedo, with a presentation entitled Graphs for Collaborative Robotics, Flexible Task Simulation and Control. So Ana Marisa Macedo, Machado Macedo, the complete name, or Marisa for short. The floor or the screen is yours. Whenever you're ready, you can start.
Thank you. Okay, so I'll start by apologizing, but I also need to turn off my camera while sharing my screen, because otherwise my network will crash. So sorry for that. I'll start. Are you seeing my screen?
Yes, perfectly.
Thank you. So, hello everyone. I'm going to present my project that I did throughout this summer internship on DIGI2, named Graphs for Collaborative Robotics, Flexible Task Simulation and Control. In the modern factory, collaborative robots have been used to work together with humans, and most of the tasks performed by these robots can be discretized in granular operations, facilitating the planning process of a task and allowing for the exploitation of joining simple commands instead of programming complex ones. Given this, this project aims to simulate the completion of a task by a robot, a human, or both, generating a graph of operations. This graph should be generated automatically and encapsulates the different operation sequences that can be performed, having as input a series of parameters of the process. But why graphs? A graph is a structure composed of nodes and edges that relate those nodes to each other. In the context of this project, the nodes represent a task, which is divided into more specific subtasks, which in turn are divided into a set of granular operations. And the edges define the sequence between two operations or the division of a task into subtasks. For example, in this graph, the task is to build a roller with 2 wheels and 2 discs. And for that, we need to bring and mount all of them. That is more specifically to pick and place them in certain positions. Each node should be composed by attributes such as its identifier, its type, task, subtask, or operation, its state, that is, the node can be still to be done, being done, or already finished. Each state is represented by a color, to do by gray, doing by yellow, and then by green. Other attributes are the operation itself, for example, pick, and the object wheel. Tasks and subtasks should also have its sequence, that is parallel or sequential, that define if its children nodes, that is its operations, can be done in any order or not, respectively. The operation nodes should also have the actor who performed the operation and the estimated and actual performance time. For this project, 2 modular furniture construction cases were studied, more specifically the construction of a table and a chair. At the left, we have the example of a table with 4 legs, 1 base, and 8 brackets. And at the right, we have its graph with the subtasks for bringing the materials, building the 4 legs, the base, and at the end for assembling everything. For this chair is almost the same. We have the building of a small table below, and we just need to add its back. So the graphs are almost the same. We just need to add basically 2 subtasks. With these 2 examples, we can see that the potential of a graph for better understanding and planning of the process of a task, being easy to use the subtasks and sets of operations for different tasks. I'll also need to highlight that some operations cannot be done by the robots. For example, operations involving fastening screws that are represented by yellow in these graphs, and even in fully automatic simulations that is only done by robots, these operations must be done by humans. So, as I mentioned at the beginning, the program needs some inputs for the process, such as the bill of materials, that is a list identifying all materials and components required to construct a product, as well as instructions for the process. We also need the initial object's pose and the final pose, that is the pose which the objects must be placed by the robot at the end. We also need the automation mode, fully automatic or fully manual. As I said before, fully automatic, the tasks should be done only by the robot, and fully manual only by the human. The operator's expertise, beginner, intermediate, or expert, this influences the time he needs to perform an operation and the probability of failing one. And last but not least, the graph in a JSON file with the tasks, subtasks, and operations, its attributes, and the edges. Here you can see the implemented graph. Here is doing a subtask. In yellow, as I said, are the tasks, the operations that are being done. And yeah, so for this simulation, the program randomly chooses a subtask to be performed, and its operation starts sequentially to be triggered, moving to the doing state. So in each operation that is triggered, if the actor is the robot, it sends the command and the position to which the robot must move to the UR5 API. The API connects with the robot. In each case, I used a simulator of a robotic arm because I was already on Erasmus and I wasn't able to connect to the robotic arm that was on the lab. Okay, after sending the command to the robot, it waits for it to finish and moves the node to the done state. If an operation is not successful, the operation is redone, continuing on the doing state until successful. All the simulation's failures can be seen in the final simulation log file. Whenever there is an actor exchange between two consecutive operations, a time delay must be added in order to approximate with the real interaction in the real world. And this visualization of this time delay is represented by a node called wait, having as attribute the delay time in seconds. After the simulation, there are some outputs. The task is completed by the actor. The graph in the JSON file is updated with its attributes and new nodes or wherever, and a log file. There is a text file with the title of the simulation mode, automatic, manual, the total process time in seconds, number of operations performed by each actor, time of activity of each actor, sequence of operations and its duration time, and the failures. As you can see here, on the two error lines, the operator tried to fast a screw 2 times, and only on the third try was successful. There are also implemented some utility functions to get some nodes attributes or set node attributes specifically for the sequential and parallel nodes. The technologies used were Python, Matplotlib, and NetworkX that I've never worked before, so it was challenging to understand this technology. And Python was for develop the program itself, and Matplotlib and NetworkX for creating and manipulating and visualizing the graphs. For future work, it is programmed to add a mixed simulation besides the fully automatic and fully manual to dynamically generate and update a graph that allows two actors, robot or human robot, to collaborate together in the same task, and when adapting to the choices and mistakes of the other, simulating the execution of all the logical paths of the collaborative process. I can also do the graph intelligence, which means the use of artificial intelligence methods on top of the graph in order to teach the agents which node to trigger or add according to the behavior of the second actor. Thank you for the attention. Thank you everyone for helping me throughout this month and making this internship a really nice internship. And thank you for Liliana especially for helping me. And that's it.
Thank you very much, Marisa. So yes, thanks for the nice presentation and for the animations as well. It's always tricky to basically present your work when you have simulators, but mainly when you have a large graph as you presented. So it's a little bit difficult to to collapse everything into a smaller area when you have such complex tasks and collaborative tasks in robotics. Yeah, so it was also related with robotics, this internship, a little bit different from the previous one, but challenging as well. And yeah, this is, in my opinion, a very good, as you said in the last slide about graph intelligence, it's a very good baseline. So you have implemented all the base rules, all the work conditions, let's say, of the graph, all the restrictions, constraints related with tasks, operations, so all these dependencies between I would call it the semantics of collaborative robotics. That's how you formulate your problem, you formulate your actions in the shop floor once you have collaborative robotics. And obviously this is not tied to human-robot collaboration only, as you mentioned, robot collaboration, which is, or in my opinion, I'm very fan of robot collaboration in this case, or robot collaboration. So as many robots collaborating with themselves, for me, it's very good. And yeah, thanks very much, Marisa, for your presentation. I also asked Liliana if there's any comment, any feedback that she wants to give, or any question to Marisa. Liliana.
Thank you, João, once again. And thank you, Marisa. Thank you for the presentation. Thank you for your work. You already know I have a place in my heart for graphs and robotics, so love your work. So I have many questions, but I will try to do some of the most important very quickly. First, and I think you did not emphasize this, that's why I'm giving you the opportunity to do so. One of the functionalities that you developed was basically a way to load and save and in several moments of the process the graphs. So I would like you to tell me, why do you think this is an important function? What do you think it allows in a process of robotics to have this type of graph process and allowing it to load in a certain state of the process, or create a new one, or reuse, for instance, already done graphs? So if you want to talk a little bit about this functionality.
Yeah, so as I mentioned in the PowerPoint, there was an input that was the graph. And a functionality that I didn't mention was that this graph can be loaded empty, or that is, if it's empty, the process is started from the start point, and at the end of the simulation, the updated graph is updated in the log file at the end or in the middle. So after a simulation, another simulation, you can load a graph that is already in the middle of a simulation instead of an empty one. So yeah, that's it. You can reuse a graph for other simulations and start on the middle point of a simulation.
Thank you, Marisa. I think that's a great functionality. Like the example you showed, you have a table and you have a share, and if you have already a graph done for the table, like you showed, you only need to add some parts of the in the graph to allow to complete the share. So being able to load a pre-done graph or even a graph that is already in the middle of the process to be able to continue a process in a given state, it's a great functionality, and I think it was a good idea and a good development from your side. One of the things, now the last question, and I think it's a question more related with what you'll be doing in the next stages of your work regarding the mixed simulation and most importantly the part of graph intelligence, like João said. I think first I would like to emphasize the the beauty of it, because you may have like a pre-done graph like the one you showed, and then all of a sudden, let's say one of the robots in the team messes up and drops a piece, or the human faints and drops all the product. So let's imagine the worst case scenario, the idea of a graph intelligence and what you stated as future work. I think it's a great thing to develop, and basically to allow for you to, like you said, not only know which nodes to trigger, but which nodes to add in the graph and where to add them in order to compensate those errors, those mishaps in the process. So my question for you, or my not exactly a question, more a thing for us to discuss, is what do you think will be I won't say the most challenging, because challenging both of the things will be, but what do you think it's better for the process in terms of general applicability? You having a graph and having an agent that knows which node to trigger according to the other actor performance, or having already, let's say, a pre-staged definition of which node to trigger, but if something goes wrong, adding a new node to the graph and basically changing the process? What do you think will have more weight and more impact in the simulation and in the process of robotics?
Okay, thank you for the question. This crashed a lot, but I think I understand the question. So the easiest one, I think, will be the one where we have all the paths from the beginning, and if something goes wrong, we can change the intelligence as the intelligence to change if something goes wrong or not as expected. So I think apart from easy, it's also reliable and easy for visualization. So I think I'll start by that one.
It's strange. You thought that one was easy? I don't think so, but we'll see. We'll see. Yeah, but I think that concludes at least my comments. And once again, thank you, Marisa, for your work and the great presentation. And hopefully, we'll continue the great work from now on.
Thank you.
Thank you very much, Marisa and Juliana, for the fruitful discussion right at the end. Before we enter into the finishing line, I would just ask if anyone, apart from supervisors or interns, or even other interns, sorry, if they want to make any question about others' work, if they have some doubts, any feedback, or we can just basically wrap up and end the discussion here, not only about Marisa's obviously work, but from everyone's work. If there's any comment or any question, right now it's the place to do it. Otherwise, we can just close the session. Just give a few seconds for anyone that wants to manifest himself. Okay, very good. So, closing phase of this session. So once again, I would like to thank all of you interns and participants in this session. I think all the presentations were very good, very smooth. They reflected exactly what the interns have done throughout these 3 months. So that's a lot of work invested in here, a lot of thinking, a lot of sweat, and I hope a lot of fun. I hope you all enjoyed your internships, and for the ones attending this session, I hope you obviously liked and enjoyed all the presentations. And just as a closing session, or a closing part of this session, I would like to invite all the interns and supervisors to turn on the camera so we can basically have some sort of print screen of the event. Since most of you or all of you are in Erasmus right now, it was a little bit difficult to have you all here on board and basically take a picture with everyone. Unfortunately, Eliseo is in another meeting, so this is then lab dynamics, you know how this works, a lot of meetings, a lot of things to do here. But yeah, let me see. So I have this very interesting together mode here in my PC. So I will now take the snapshot. Let me wait for it. Give your best smile, and no, I was sorry. I was too bad. Let me just check one thing very quickly. And Marisa, I'm using Paint, you know, so it's a great tool for graphs, not only for graphs, for everything. But yeah, so 1, 2, 3, cheese. No. That is There you go. Let me take the worst in you. Yeah, exactly. Let me take the worst in you. Okay, very good. So I think we get it finally. Now that we have all the cameras turned on, which is more personal, let's say, thank you all for your effort on this. I hope you really enjoy this. I think it was tough because internships need to be tough for you to grow a little bit up. But I hope most importantly that you enjoyed this. I hope this also opened some new opportunities for you, either for your dissertations or for the market that comes afterwards, that you learn good things either in robotics, in machine learning, in explainable AI, different topics. So I really would like to thank you. Personally, I spent a very good time with all of you. Obviously, according to my area, I spend more time with some interns than others. But yeah, I mean, all the supervisors followed your work, advised you as much as possible. So thank you very much. And yeah, we'll see you soon physically, just a little bit in a few months. Okay, but yeah, we'll be talking about the next steps. Okay, thank you very much.
Thank you.
Thank you.